Welcome to Brain Vision.
So we're trying to find a diving bell that can withstand a pressure down to 250 meters. So the gauge pressure at this would simply be delta P equals the hydrostatic pressure minus the atmospheric pressure. And this is going to be simply the density of the water times the acceleration due to gravity times the height or the depth of the water. Here, it's going to be delta P equals 1,000 times 1,000, the density of water, 1,000 kilograms per meter cubed, times the acceleration due to gravity, 9.81 meters per second squared, and then times 250 meters. This is going to give us a gauge pressure of 2,452,500 pascals. Now, at this point, they're asking us what is the force due to the air inside of the diving bell and the water outside of the diving bell, given that the pressure inside of the diving bell is equal to P sub O, or the atmospheric pressure. Here, this is simply going to be a force equals the pressure at this depth times the cross-sectional area, or rather just the area of the cross-sectional area of the bell, which is simply just the area of a circle. Here it's going to be 2,452,500 pascals times pi times the radius squared. And the radius here is going to be, we have the diameter of 30 centimeters. So that means that the radius is going to be d over 2, or 0.15 meters. So here we can put 0.15 meters squared. And we find that the force here is going to be 173,357.01 Newton. So this would be the pressure, the force due to the air inside of the diving bell and the water outside of the diving bell. And then this is simply the pressure, the gauge pressure at a depth of 250 meters. And that's the end of the solution. Thank you for watching.